Hi
So, yeah.
everyone, welcome to our 11th CUDA Mode lecture here on the CUDA Mode Discord server. Today we have a special guest, Jesse Kay from Meta, who's an expert in different architecture optimization techniques and especially quantization and pruning. So this is a very interesting topic. I think it's a little bit underrated right now because we have so great GPUs which can do dense matrix multiplications so well. But from quantization and different things like the lottery ticket hypothesis, we know that there's a lot of things which could be set zero or could be omitted in the weight matrices of neural networks. And yeah, I think there's a bright future for these kinds of pruning and quantization techniques and sparsity in general. So yeah, the talk today will be about sparsity, and I'm super happy to have Jesse here. Jesse, if you are ready, please go ahead and start.
Sure. Yeah, thanks for the great intro, Andreas, and thanks everyone for coming. Yeah, I'm here today to talk about GPU sparsity. So I guess first I can tell you a little bit about me. I work on the PyTorch core team on architecture optimization. So if you guys remember Charlie, Charlie is one of my teammates. We work on quantization slash sparsity, particularly in the last 2 years. It's been mostly focused on Gen AI, like LLMs and vision transformers, and been focusing on bringing these techniques to GPUs. Before we were mostly focused on as a team on edge stuff and CPUs, and then now because the models are so big, right? We have to run inference on GPUs, and we'd like to take a trained model and be able to cut some of the weights out or make some of the weights a different lesser D type to the performance of the model at the expense of some accuracy. And the idea is that if we're clever about how we recover that accuracy, that drop can be negligible. Um, and then just some contact information if you want to get in touch. Yeah. So what is sparsity stress pruning? The basic idea is very simple, right? Waste compute, use many parameters when you don't need that many. And there's really two parts to this, right? So basically you have your original neural network, right? And then you've trained it and you have a good set of weights, right? And then what you want to do is to remove some of the weights. And the idea is that if you do this in a clever way, right, and recover, you can do it without affecting the model accuracy. For example, if your model is just a simple linear layer, right? If your weights are 0.001 is 0.1, right? That 0.001 weight doesn't really do anything. So if you remove it, you can save on some computation, right? And it's not going to affect your outcome if you're doing something like classification, the logits won't change, right? So you'll be set. Um, so essentially, the first step is to zero out the weights. And then there's a second step, which is that you have these zeroed out weights, right? Make multiplying by zero fast. And that's really the core concept of sparsity is how do you accelerate that? And this idea is not that it's been around for a long time. So it's the oldest paper that I think people reference is this optimal brain damage paper back in 1989. So it's been around and with the AlexNet and the ImageNet stuff that happened in 2012, there was a lot of re-interest into this, but now especially with the LLMs and AI and the model sizes just becoming so large and so many parameters, right? That there's kind of renewed interest in this and quantization and other techniques like that. So yeah, that's sort of a intro into sparsity. Any questions before I move on?
So far,
Cool.
we have no questions from maybe. So if everybody, if anyone has a question, please use the chat, which comes with the stage channel, and I try to then forward them. Thanks.
Yeah, so now we get to the performance part of this, right? So for sparsity, right, the idea is that multiplying by 0 is fast, right? So example, I have these two numbers, right? 0 times 1,200, whatever, right? And I know that's 0, so I can do that calculation fast, right? But if you ask me to do the calculation on the right, I can't do this fast. Oops, fast, right? But also, like, how I do that calculation matters a lot, right? So, like, I do long multiplication, like the way that you're taught in school, right? With like 1, 2, 3, 1, 2, 3, 1 on the top and 0, and I'm like 0 times 1, 0, and then you carry, and then you also times 0 times 2 is 0, and then you carry, and you keep on doing your calculation in the same way, right? Then actually multiplying by 0 is not going to be any faster. It's going to be marginally faster, right? But you're not actually saving that much time on your calculation. So like this is the idea, right? So you have to have a way to multiply by 0 that's faster, that skips out the calculation. And this is in the instance of a single t, right? A single number, right? Like how do you take that and apply it to a tensor? Like what does it mean for a tensor to be 0, like highly sparse? Like if there's 99% 0 and there's just one element that is non-zero. Yeah. So that's sort of like what we get into with like sparsity is like different sparsity patterns, right? So like there's kind of like a trade-off, right? Like we want a lot of flexibility, right, to minimize, the accuracy impact we have by removing zeros. But at the same time, like we want to be able to do uh, computation fast, right? And if you have this sort of unstructured, really random assortment of zeros, it's very hard to speed that up versus something like, for example, like instead of zeros, um, do not see slides. Yeah, instead of zeroing out like randomly, right? You can zero out an entire layer or an entire like part of a network, or even like an entire row. Okay, it's good to know slides are good. Or an entire layer, or like a row or a column, or like a filter if you have a CNN, right? That's the idea of like structured sparsity. And there, right, you can make the computation a lot faster, easier because you just don't do it, right? But then what happens is your accuracy impact is really high because you're taking like an entire layer out of a network, right? And being like, you can recover that information, but you're removing a lot of information. It's sort of like this trade off between, preserving accuracy and having good performance. And sort of along that vein, there's sort of intermediate representations for sparsity, specifically for GPUs, like semi-structured and block sparsity. And then those are the things that I'm working on really for like the last couple of years. And um, yeah, those are the things that I'm going to talk about today.
So quick
Yeah.
announcement for the people who say that they can't see the slides. So we had this before, and yeah, when we tried to resolve it by like stopping and restarting, it didn't really resolve it. So this session is recorded and will be released really soon after the recording. So yeah, I'm really sorry for this things which are like Discord problems. I think some people can see the screens and hear the speaker. If it's not possible, then please wait for the recording, which will be available soon. Thanks.
Cool. Yeah. So, for example, right, I'm going to talk about unstructured sparsity. So, like, unstructured sparsity is like when you have no constraints on where you put your zeros. So it's basically just like a mask, right? And like, so like if you have a that's like a lot of zeros, like how do you make multiplying by that tensor fast, right? The answer is that you store the data in a sparse representation, and then you use sparse kernels instead of your dense kernels. So like instead of doing your long multiplication, right, you do your fast sparse multiplication, and you have your shortcuts to cut out computation. And sort of what this means is like you want to store the data, the structure independently. So to kind of illustrate this point, I have this example of coordinate representation. This is one of many sparse formats. Sparse like documentation has like a list of all the ones that are supported. If you guys are curious about like the different ones, and basically you can see we have this matrix, right? 1, 2, 3, 0, 0, 0, 0, 0, 0, a 3 by 3 matrix. And usually how is this stored? It's stored contiguously in memory, right? And you just have your offsets, so you know like your strides and stuff. Then for the compressed representation, right? How do we store that? Is instead of storing the all of the elements with all of the zeros, right? We just store the non-zero elements, right? And we store the data for that element and the index for that element. So we store 1, right, as 1 in the data elements, and then also 0, 0 in our indexes, right? And then 2 in the data elements, and then 0, 1 in our indices, and so on. And you can see how if your matrix is sparse enough, right, multiplying in this way is a lot faster. What you do for multiplication is you just generate like a zero matrix, right? And then you just go and you look at your index, right? And then you just do the multiplication for the parts that are non-sparse, update in your subsequent resultant matrix. And that way, right, you can speed up your sparse matrix multiplication. And so this is sort of like how like CPU sparsity works. It's only really faster at high sparsity levels, like greater than 99%. And it's because that you need to be faster than doing like the actual dense like matmul. And the thing is if you think about it, we're like GPUs, right? Like it's even worse because dense matmul is so much faster because it's easily parallelizable, right? And then GPUs run in parallel, right? So what that means is that this kind of unstructured sparsity is even harder, like to make fast on GPUs. So it doesn't really work. Like you think you could make it work. Essentially, you have to figure out a way to preserve some sort of structure because you are using like parallel architecture to solve this problem, right? So, like if you get it down to a singular element, like it's not going to help. And like if you remove stuff so that the blocks are basically, yeah, if you remove stuff, um, arbitrarily, right, that's hard to parallelize on GPUs. So how can you get around that, right? That you can do the stuff I was mentioning earlier about structured pruning, right? But you can also use these sort of intermediate sparsity patterns. So there's like 2 that in particular that are available for GPUs. First one is semi-structured sparsity, which is also known as 2-4 sparsity. It's basically a fixed sparsity level at 50%. Like for unstructured block sparsity and structured sparsity, the sparsity level is like variable, right? So you can just pick whatever you want or pick the thing that is faster but like maintains the most accuracy. For semi-structured, your sparsity level is fixed at like 50%. And then what happens is you have 2 and 4 elements are 0. That's where the 2 and the 4 comes from. And the nice thing about this, right, is that NVIDIA has done a lot of experiments that have shown that there's a very easy way to recover accuracy for these models where you just train once or you prune once and then you retrain. And that seems to be doing good. And the other sort of sparsity available for GPUs is something like block sparsity. So the idea here is pretty simple. Instead of having just zeros everywhere, right, you have zeros in a block, like 32 by 32 or a 4 by 4 block. And those blocks are spread out, and you keep track of essentially your each block. And then for the 0 blocks, right, you don't have to keep track of those. So like the downside here is for block sparsity, the algorithms to kind of and recover accuracy are more complicated, and it's a much more like open like research problem where there's not really a good like known like solution. Yeah. So I'm going to talk a little bit more about semi-structured sparsity here. Basically, you can see how with 2 in every 4 elements being non-sparse, right? You can see how like the dense values are pack them together to be like half the size. of the original tensor. And then you also have to capture the structure, right, of the information of the structure that you lost basically by compressing this all into a dense tensor, right? Because you lose information if the white ones were the ones that you kept instead of the ones that you removed, right? Then you wouldn't be able to tell like where it happened in this block. And what you need to recover that information is these it's basically like a bit mask, but it's compressed. But it's basically 2 bits for every element, and this captures sort of the mask implementation inside the sparse matmul. So yeah, this is like integrated into PyTorch. You can try this and use it right now. For like the backend, there's like 2 different ways you can do this. Like you can do this in Cutlass with the original like instructions, and then there's also an NVIDIA specific library called like QSparseLT that provides some like additional features and makes it faster and a little bit easier to use. So yeah, we have both integrated into PyTorch. We're kind of like deciding which one to pick. But yeah, just wanted to let you guys know if you see like QSparseLT or stuff, that's what it's about semi-structured sparsity.
Just a question to this specific sparsity format. Is it
Yeah.
so? How do you normally like select those elements which should be specified? Is it just that you set
Yeah.
look for values which are very like small, or is it that you take gradients and so in this case specifically you need to like you know in advance like how many you will basically discard of each block, and you will it's
Yeah.
yeah. So how,
Yeah. So I think, yeah, to answer your question, like, how do you pick which elements to remove, right? That's kind of like active area research, but like for most of like what we do, it's just like the lowest weight norm values. So you just take the absolute value, and all the small stuff you remove, essentially.
yeah, okay, that makes sense. And you hear this like 1.6 on average in practice. This is
Yeah.
like a kernel dependent thing, or is it? Do you know, or do we know where this limitation comes from? Where it's not actually 2 times
Yeah.
fast?
So the 2x max acceleration makes sense, right? Because you're having the values. The 1.6s is like basically it's a lot to do with the shapes of the matrices that you're multiplying. Like depending on the dimensions, you have big M versus big K versus big N, right? Like the speed ups differ. So like I don't remember exactly, but I think you want a big K dimension and a small N dimension, I like ideally for the fastest speed ups. But if that's not the case, right, then you kind of have, slower speed ups. And I think that's the overhead of, loading the metadata, which is the bit mask into your matmul operation. And the 1.6x is sort of like a kernel benchmark. So just like compared to the dense kernel.
Okay, thank you.
Yeah, and this is just showing how this matmul works. You have A dense and then A pruned, right? Removing, the weight norm values, and then you compress it. You have the metadata too. It's not shown here, but it's part of this tensor. And then you pass it to your matmul with a normal dense matmul, and you get a dense tensor out. So basically, all you do is you sparsify one of your elements, and then if you can make it so that dense is already like the zeros are already put here, right? This is numerically equivalent to matmul with the zeros. Yeah. So just sharing some like end-to-end results that we've done. Um, we've on the table on the left, these are the NVIDIA original like results from their paper. So they did a lot of stuff. This came out in like 2020, so these aren't the newest models, but they did a lot of stuff with like vision, and they've shown that like the simple one's retrain strategy, right? The sparse FP16 accuracy and the dense FP16 accuracy are pretty much equivalent, which is nice. And then what we've done, right, is we've applied this to SAM like last half, and that's been like pretty good. So for 2.4 sparsity, right, we get a 1.4. Yeah, this is not the speed up, but see, we get 23 images per second versus, um, I guess the equivalent would be 20 images a second, right, for the non-sparse version. So we get a speed up of like 3 images per second. Um, yeah. Uh, any questions here?
So we have one question from Drexel. I'm not sure if I understand it correctly. It says, what parts of the VIT
Parts of
are the
it
sparse?
are this for? Oh,
Do,
so
do you know
basically
what he means?
yeah,
Okay.
yeah. So the VIT is not sparse initially, but we can make it sparse essentially, right? You can make it sparse by removing the weights, right, um, that are low magnitude, and then just trying to retrain and recover the weights, recover the accuracy, right? So essentially, what you do is, right, you have your original weights that are not sparse at all. They're all dense. They're all like non-zero, right? And then you find like a mask that makes it fit the sparsity pattern, right? And then you keep on training, and then you hope that you can recover the accuracy in the other values. And the way that you find the mask, right, is by using some technique. Like the simplest is just using like weight norm pruning, which is just the magnitude of the like the absolute value of the value. Yeah, it's not. It's you can apply this to any linear layer right now, or really you can apply it to any map mol. It's hooked up, so it's very easy to do for linears. Just doing torch.tensor, I can show you. Yeah, and so like for if you want to do it into the MHA, it's going to be more work, right? Because unless your MHA is implemented as like a bunch of linear layers, the fuse thing, then you have to go into your fuse kernel and then actually like replace this map mol with the sparse map mol, and that's a pain. Yeah. But if you want to just do it to the linear layers, right, then you can apply those instantly. And yeah, you can see like this is sort of our code. And top part apply fake sparsity is just the bit that zeroes out the weights. And then once those are zeroed out, like how do you actually accelerate them? Um, right, that's just this line here, like line 31. If you set mod.weight is equal to torch.nm.parameter, and then you go to sparse semi-structured mod.weight. And this will take your weight and put it into the compressed sparse representation. Um, yeah.
Just this one question. You mentioned like this, like the
I,
vision transformer case, that there you continue training. Is like in the sparse model, is this like a general approach that you do the specification and then also have training, or is it like
yeah.
that you normally there are other methods to have like sparse, I don't know, sparsity inducing training or like
Yeah.
sparsity in aware training or something like that?
Hmm. Definitely. Yeah, I think definitely all those methods like exist. Like I think it's kind of like an active area of research. Like basically what's been happening is that there hasn't really been like sparse kernels like available for GPUs. It's been very hard to show speed ups. Like almost all the papers until like recently have been showing just like the accuracy side. So like I don't think there's been as much like interest, right? Because if you have to work super hard to show like speed ups, right? Like that's really what people want, and it's like you have to like set up Sparse LT yourself and like hook up it. Like nobody's really doing that. So I think yeah, it's kind of like open. Like there's like zero shot approaches too, where you don't do anything, and like one shot approaches where you um, kind of do like just one pass, like a calibration step almost for like quantization, something akin to that, where you calibrate on some data but you're not fine tuning. Yeah, so there's a bunch of approaches.
A few moments later.
This out, it's a very simple API. Just using that, it's nice. It uses 10th subclasses. It's compatible with torch.compile, which is really nice. actually for torch compile, it's actually kind of necessary. So something that's kind of annoying about current semi-structured sparse implementation is that it only supports the first matrix being sparse and not the second matrix. And for us in PyTorch, the way that the linear layers are defined, it's XW transpose instead of WX. So this is kind of annoying, but we can rewrite it, right, using transpose properties. That's what I've shown here, right, as WX transpose and then the whole thing transposed. But the problem is that if you have this additional transpose, right, it will eat into your performance, right, because you have to copy back into your memory and then back into your GPU, and then you do the transpose. So with Torch.compile, right, you can fuse that transpose into the subsequent operations. Like if you have your ReLU, right, basically you have, you know, sparse MM and then transpose plus ReLU, and then that whole thing together is much faster end to end. But unfortunately, right, with Torch.compile now, right, you can't fuse into the sparse MM. That's kind of a problem I'll talk more about later. Yeah, so that's part of what we're doing is semi-structured sparsity and what I've been working on mostly. There's another sort of thing, sparsity pattern like block sparsity that we've been investigating recently. So basically, we found that some people were able to recover the accuracy really well using the technique like dressed I linked in the earlier slide. And the nice thing about block sparsity, at least for vision transformers, is that we can get much faster than a 2x speed up, right? Because we have a very flexible sparsity level. Like I think with like a 90% sparsity, we get up to like 3.4x. And sort of our ET result is we can get a 1.4x speed up with minimal accuracy loss on ImageNet for vision transformers, just 2 percentage points.
Wow, that's crazy. So is 90% something is a normal number? So like something which works often, also often the case that you have only like very low accuracy drop for zeroing out 90%.
I think yeah, the accuracy drop I would say is like this is pretty expected. I guess now that everybody can see our slides, go back to Sam VidH on Coco 2017 eval. This is actually zero shot performance. So this is 2-4 pruning. You don't retrain at all, and then MI over U for Coco 2017. So it's like 90% of the way there, which is pretty impressive. Like it's definitely not something I would expect. And I think this is specific really to vision models, that this 2-4 sparsity seems to be very amenable, maybe because of like locality or something. For example, for LLMs, if you do the same thing, like zero shot pruning on some like sentence classification task, like your accuracy is probably going to be like 0.01, like, and before it might have been like 80 or something, just, or like maybe not that drastic, but you're definitely not getting like close to like 90% with like zero shot. Yeah. Yeah, I think also like this is something that's like kind of we're like looking into now, is just like we really should just fine tune on yeah. All right, I'll finish this and then I'll answer your question. We should really just fine tune because this is like a very simple recipe, right? And we just haven't done it because we've been kind of lazy. So if anybody wants to like do that and give it a shot, like I think you can basically get this accuracy back into 58.46, and you just have to try it. But yeah, yeah, there's a tutorial for BERT, but you just take BERT and replace it with SAM and then pray, and then hopefully you'll get it. And yeah, I saw there was a question about sparse GPT work. Yeah. So yes, the sparse GPT work is very related. Sparse GPT is like basically like a one-shot calibration method. It's the idea is that you don't have to retrain, because like for these large LLMs, if you retrain, it's problematic. And the reason why it's problematic is because if you want to do masking, then you have to store the mask information somewhere, and you're already like struggling for GPU memory, right? So like if you also have to store like the mask information, right, then sort of like defeats the purpose, or like retraining. It just makes it so much harder, right? And then already training LLMs is like pretty hard. Like you can't really do it. Like you can fine tune, right? So that's why I think people have been looking into these like one shot, sort of like calibration esque, techniques for recovering accuracy for these larger models. Yeah. Cool. And then I'm going to talk a little bit about the work we were doing currently. Um, so there's basically like a couple parts to this, right? The first part is like composing with quantization, and we have some like interesting findings there. So let me share this. This is kind of informal, but I don't know if you guys can see this. Um, Essentially, like when we compose quantization and pruning together, we run into sort of a lot of issues, and kind of dealing with like torch.compile, but we're just dealing with like fusions, right? So or like a normal graph, right? You have your weight and activation and your output, right? And this is how it works. Very, very classic. And then for sparsity, right? Essentially what you have is you have your weight and then you add the zeros, right? And then you compress. Um, and then once you get your compressed thing, you get your compressed representation. And that stuff all happens offline. And then at inference time, you take your compressed representation and then you take your sparse kernel, right? And you have your output. And that's fast, right? And that's great. And then like for quantization, right, what you do is basically quantize to an int8 or like in a lower dimension d type, right? And then you do int and then you have your output, right? And then you requantize into your floating point or higher dimensionality d type. And the nice thing with torch.compile and what Charlie's done in his work is he's you can fuse all of this together, right? But the problem with adding, sparsity to this mix is that you can't fuse into the kusparse LT or like the cutless stuff unless you write a fuse kernel. Um, but for kusparse LT, you can't fuse into it at all because it's basically a black box. What you will have is like a fuse bit, a kernel, the kusparse LT call, and then another fuse bit for the dequant. We found that basically that makes it slow. So if you look at these numbers, right, baseline for BF16 is 1600, right? If we apply sparsity, we get down to 1400. We see a nice speed up. That's great. If we apply dynamic quantization, right, we see 1400, which is like a nice speed up. That's great. If we apply both, right, we should get, what is it, 1200, I guess, if it was the perfect world, right? But when we apply both, right, actually we see a very marginal speed up, if nothing at all, right? Like 20 milliseconds. And the reason for this is the sort of operator fusion stuff talking about. And what we can do is like basically we can, for kusparse LT, we can fuse a little bit of the dequant into the kusparse LT matmul because they have support for like alpha vectors. So you do that, right? You can only fuse one of the multiplies. There's two multiplies for the requantization step, but once you do that, right, you get a much faster runtime, like 1,278. So yeah, this is kind of like of the interesting work now where there's like a lot of problems where, for example, like doing this with kusparse LT, right, you can only fuse one of the fusions, right, and you can't fuse anything else, right? If you were to do this in cutless, which you can also do, right, then you could, write a fused dequant epilogue, right, for both of the multiplies, and get speed ups that way. And similarly for cutless, right, if you wrote like something, you could write a fused kernel for the transpose too. So like for kusparse LT, they have support for merging the transpose as part of the kernel, like as one call, and that's not something we support for cutless currently. But if we were able to add that, right, then that's something that would help us, push this like performance numbers up, essentially. Um, yeah, and I think also there's sort of like an accuracy component to this, too. That's like kind of interesting. Um, and
So is this
basically,
is this in
yeah,
general like in we see the like slight performance increments, or you get a little bit better performance using sparsity and quantization together. But is it like worth it? Is it really because I would like assume now you zero out all this element and then you like remove all the bits and in the end it's like becoming really worse and it's I don't know, is it before you show now some accuracy.
yeah. I think it can work. So like for example, the the accuracy is degraded quite significantly. So I can show you a slide, which is um, sorry. Let me think of how the best. Yeah, the sorry. Can you ask your question
Yeah, so
again?
the question was basically
Yeah.
like, is quantization plus sparsification a winning team, or is it like still an experimental,
Yeah.
very experimental phase right now?
I think yeah, from a performance perspective, it's winning. From an accuracy perspective, it's kind of like up in the air, for people to figure out. Like, yeah, like this int8, like quantization stuff, we haven't done any accuracy experiments on, um, you know, on the actual that side, to figure out if there's like a huge accuracy impact or not. Because like basically we're mostly focused on performance stuff. So like any accuracy work we do is just like zero shot and then just making sure it looks all right. And we haven't invested time in like actually fine tuning and trying out like different techniques and like I think there's a lot of active research, right? And I think people are kind of like looking into this. The Sparse GPT paper actually I think has a section on composing with quantization, and I think some of their results are kind of interesting. Show that, like, for example, if you have like 4-bit quantization and then you go to 2-bit quantization, instead you could do 50% sparsity and like 3-bit quantization, and those lead to better results instead. But I guess like you can see how like you can play with it, right? You can quantize to more or less bits and then like sparsify to more or less stuff, and just kind of go around that way. If that makes sense.
But is accuracy the gold standard to measure the quality of the quantization or the specification, or are there also other metrics like I don't know KLD versions or several like loss metrics or so that you look at?
Yeah,
Yeah.
I think there are for like quantization. There's like SQNR, like quantized noise ratio. Like I'm imagining there could be similar metrics that you could use for sparsity. Actually, something we've been talking about is like evaluating for sparsity. I don't know if we necessarily have the right approach with like accuracy. Really, since you have the original model too, you can just do maybe some agreement score, and that's a better
Mhm.
metric of how well your model captures your original model. Yeah, I would say like for us, that's probably something that we haven't really like thought about. Like for us, like the accuracy stuff is like really like back of mind. Like we're just focusing on getting like the performance and showing that like, hey, if you figure out the accuracy stuff, right, then you will get the performance. Like the way I think about it is basically like, like the clown dunk tank. We built the clown dunk tank, and then now like all the researchers have to throw their shots and try and dunk the clown. And like if you hit it right, you're gonna win, because like we've shown on the performance side, right, that there's up to this like 2x, and we can keep on pushing it, right? And like we know it's numerically equivalent, right? If you put the zeros in the right place, the sparse map mole and the dense map mole will give you the exact same result. So you just have to figure out where to put the zeros, and you can hopefully win, like get all the performance stuff. So yeah, I hope that helped.
Yeah, I guess also for classification, it's like the most important metric that you want.
Yeah, I think the thing about accuracy is it's just easy to tell, right? Like if stuff goes up or down. Yeah. Um, yeah, I think there's also the work we've been doing with like sparse training. So we've been talking about this in a context of like inference, right? Just like offline. But since like in actuality, you're just speeding up a matmul, and like the matmuls happen during training too. So we could also speed those up. And for quantization, like for training, we don't have to worry about quantization at all because that's not really something that we're doing, right? And then be a way to speed up training. So this kind of works. The idea is that you have a very fast way to sparsify the kernel, and you do it with like weight norm, like magnitude. But since it's a 4-element thing, I think you can do it without sorting or like without branching, essentially. And if you do it that way, it's very fast. Essentially, what you can do is you can sparsify, run your sparse matmul, and get your dense result in a shorter amount of time than just your dense matmul. Like in inference, your sparsification step happens offline, so you don't have to worry about that. For training, right, you have to do it all at once, right? And then that step is faster than your dense matmul. And Formers is a team, we've been working with them. They've basically written the fast sparsification kernels, which has been really helpful. And then they've done some experiments with, um, ImageNet, showing like a 10 to 20% speed up end-to-end training with like a very small accuracy gap, 81.6 to 80.5. And there's kind of like a lot of like nuance here. Like they apply to the activations versus the weights, and that has to do with like the matrix shapes and also like the activations. Since they're coming after a ReLU, right? They tend to be more sparse. So I think there's a thought that it affects the accuracy less there. Um, yeah, yeah, some results. Yeah, I won't go into this too much, I think. Okay, yeah. There's some differences between inference and training that I think are kind of interesting. So in training, basically, what's really tricky when you have the compressed representation is doing a transpose. If you do a transpose, you can't really do that on the compressed representation. Versus on the dense representation, the transpose is essentially for free, right? Because you just switch the strides and then you're set. But with the compressed representation, since the structure is all stored, you can't really switch the strides. There's nothing analogous to that. So since we need both W and W transpose for training, right, for the forward pass and the backward pass respectively, what we do is we just keep a copy of, like we keep the compressed representation of W and compressed representation of W transpose. And this means that there's not as much of a memory benefit, right, for semi-structured sparsity. For inference, there is, but for training, right, since you're keeping both, you actually have a slight memory penalty. It's just like a pure compute play. And another difference is that for training specifically, you need that fused transposition thing that I was talking about, and that's only present in cuSparse LT. So for training, you need cuSparse LT in order to get the speed ups. With cutlists only, it won't work unless you add that functionality. Yeah. Yeah. Cool. I'm just gonna skip this. Yeah, and then I just wanted to talk really quick about like stuff that I think is like interesting in this field. We talked about block sparsity and 2-4 sparsity, but like the reason why you can't combine them both, right? You could have blocks of 2-4 sparsity and 2-4 sparse blocks, and then that's really exciting because like that means you could push the performance like 2x times 3.4x. Like obviously it's not going to be that fast, right? There's going to be some competition, but like I think it's really exciting to think of like sparsity patterns being composed in this way. And I think there's also other like very clever stuff like blockwise sparsity is very fast, right? But the sparsity pattern is very inflexible, right? But what you could do is you can add a shuffle into your load into your blockwise, right? And that's what these people have done here. There's this paper, I'll link it in the slides. But basically by adding a shuffle, right, they have this they allow for this sort of like pseudo unstructured like sparsity pattern. Not like that actually. Like there are definitely still constraints, but you can see how this is a lot more flexible from like an accuracy perspective than blockwise sparsity, right? So like I would imagine that this would be a lot easier to do. And yeah, the shuffle, right? Shuffle is costly, right? So that pays into the performance hit, right? But with torch.compile, right, you can fuse that shuffle into the other ops, right, and reduce that performance hit. So yeah, basically, like I'm kind of thinking about it is that having these like sparse building blocks, and then you can just kind of like play with them and compose them with like a shuffle, and then torch.compile make them fused and fast, if that makes sense, and then also like with quantization and torch.compile to make those fused and fast, and just be able to like plug in like nice and seamlessly, essentially. And there's also some interesting work, like you could use 2-4 sparsity for dropout too. Dropout's already 50%, and like it's 50% random, right? But 2-4 sparsity might just be random enough, right? And you know, if you get 90% of the benefits of dropout, right, but you just you know have to have this like 2-4 constraint, right? It might be worth it. And like the idea here is you basically just generate like a random mask metadata, right? And then you pass that in when you're doing your dropout. Cool. And then I think like this is like CUDA mode specific stuff. I try to think of stuff that you guys might be interested in. Yeah, feel free to reach out if you're curious. The Cutlass Sparse LT gap, I mentioned about this. We've had somebody from QuantSite who's done a lot of really good work here. And there's basically Sparse LT is like NVIDIA specific version library that supports this, but it's a black box, and the fact that it's a black box makes it complicated to like do this sort of composition stuff, like fusing into it. You can't do it. For Cutlass, right? You could do if you wrote the Cutlass kernel, then you could obviously add stuff subsequently, right? Like for example, like fusing the transposition, we could add that into the Cutlass kernel or semi-structured sparsity. Also, like fusing the dequant into the Cutlass kernel. Also, like obviously these kernels have a lot of parameters, right? Like thread size, warp size, stuff like that. That's all fixed, right? For dense matmul, you know, that's all like configured, and there's like tuning and stuff like that, and that's not hooked up for the sparse matmul at the moment, right? Yeah. Other thing is like larger fused kernels, right? This is kind of sparse LT stuff, and then flexible sparsity patterns, right? Like writing a fast shuffle or some version of that, right, is actually like very helpful, right? Because it allows us to give different sparsity pattern to like researchers that's like a lot more flexible. And hopefully those patterns, right, it makes it easier for them to you know, the clown, I guess. Yeah. And then, you know, load as sparse kernels. This is kind of a different idea, but like if you want to do unstructured sparsity, right, you could do it in a way for llama where you're not compute bound and it's like memory bound mostly, right? You could do something like load as sparse and then expand to dense inside the GPU and then do dense matmul. And the idea here is that your dense matmul takes the same amount of time, right? So there's no speedups there, but your load as sparse expand is going to be faster than your load as dense thing. And that's how you can, you know, make a play and try and get speedups that way. Yeah.
So that will probably then for like low sparsity. So if you have less than 90% zeroed out, right? So
Yeah. Yeah.
and
I
as you
think like
mentioned,
the other,
yeah, sorry.
yeah. I was just to say, like for Triton, like Triton doesn't support semi-structured sparsity. I think they have block sparse support. So like it would be very cool, right, to be able to fuse this end to end. But like have just try to generate all the code. Like, but I think this is not very realistic. It seems like it would be like a lot of work. So, but yeah.
Yeah, regarding Triton, I actually wanted to ask, like, how easy is it to manipulate like sparse structures in Triton? Because you have like always this, or often this indirection that you need to read
Yeah.
indices, and then like compute new addresses basically on
Yeah,
this indices? Is it? I think it's possible, but have you like some
I would
experience on the
say
performance?
I would say for block sparsity, it's a lot easier. I think Python does have some limited block sparse support because the indices, like the way it's managed, is more regular. For semi-structured, the metadata format is proprietary. It's just not documented at all. So, figuring out exactly that format and how to compress into the compressed representation, that's sort of like really the tricky part. And I think that's like the magnitude of the work if you were to try to add this to try and, yeah.
Okay, yeah.
Cool.
As you mentioned, like compression, like in general, is this it's like not directly quantization, also like sparsification, but is this somehow also related that or is this also a concept of because you mentioned like loading sparse matrices and then
Yeah.
computing in dense. I think like compression is something similar, right? It's like for normally, of course, we have like JPEGs, and if we load them, if we do ImageNet training, we also have some form of decompression which takes place at this at
Yeah.
some point. But is there
Yeah.
also like concept of compression in during computations or during I don't know like it's like similar. So some sparse formats are like reminding me a little bit of like very simple compression algorithms like run length encoding or stuff like that.
Yeah. Yes, yes. Yeah. Run length encoding is like another sort of load as sparse and run length encoding, like to me, are like the same sort of like concept.
Mhm.
So yeah, yeah. I'd say, yeah, yeah, definitely. I agree.
Do you see that there could be in the future also like support? They should there be support for sparse representations directly from hardware? Could the hardware be many like organized differently to
Yeah.
simplify or improve the performance of sparse
So
computations?
yeah, so I think that's basically what NVIDIA tried to do with semi-structured sparsity
Hmm.
with like tensor cores. I think there's probably some special hardware or something that makes like this particular sparsity format like fast. And I think like yeah, like I think the hardware vendors will probably decide the true like hardware supported sparsity patterns, right? But like with like the shuffle, like that idea, right, is you could take the hardware supported like block sparsity, right, and present many more different patterns to people.
Okay, yeah, thanks.
Could I ask you a question?
Sure.
Yeah.
Maybe a two-part question. But so for during inference, you do sparsity to, speed it up and maybe save energy consumption. For during training, are you doing it like kind of like with quantization aware training? Are you doing it to like make the model more robust later when you make it sparse?
Oh no, for 2-4 sparse training, it's a compute play. So we're just trying to train faster,
Mhm.
and that's like the main advantage. That's why we want to do it. It's like we might be able to train faster slash like bigger models, like larger. Yeah.
Cool. And then the second part was, so if I understand this right, the values you choose to zero out are like the smallest ones basically. So
Mhm.
do you do the sparsity during training like later into the training, or do you just do it from the start?
So basically, what you do is you do it every time. Like you have your dense weights, right? And then you look at it at inference time, like right before you do the matmul, and then you sparsify it, and then you do the sparse matmul, and then you keep on going. So it's not like, yeah, sorry, does that help?
Yeah, but I think just like my intuition tells me like, would there be any merit in doing sparsity like, I don't know, later in the training so that you're, like
Yeah,
zeroing out the right
I
weights?
think I think yes, there's like a lot of I think stuff you could play with here, like like progressively introducing it, and then like turning it off, and like um, like gradually increasing sparsity is another thing I've seen that like researchers have done, where it's like first they do like 10% and then 20%, and they just try and keep on pushing it up. Yeah, it's kind of like there's no like wrong answer or right answer. It's people just try whatever. Yeah. Cool. Yeah, this is just my last slide, I guess. So yeah, we're building something pretty cool up here, I think. Really like make these models bigger, and I think that's really awesome. Like right now, I think a lot of the issues that we're running into is like accuracy, right? And just people figuring out how to put the zeros in the right place. And I'm optimistic that hopefully someone will figure this out. And on the performance side, right, we've shown that sparsity works, and it can be used to make stuff faster. And we can keep on pushing like this sort of like sparsity performance numbers and make it more incentive, like keep on incentivizing people to keep on approaching this problem from like an accuracy perspective. The last thing I think is like the more I think about it, I think like the accuracy and the performance stuff is really like intertwined. Like I think as a researcher, trying to find blockwise way to like prune a network is quite hard. But if you can find like like a shuffle version, right, then that seems like much easier, and like the way that you can add stuff and like have stuff fuse, right, and not pay as big of a penalty, I think is pretty interesting. Yeah. Um, that's all I had today.
Super
But,
cool, Jesse. Thank you very much for these like details and insights into